Hey guys, good morning. Um, Go ahead and let me know who's here. All right, thanks for tuning in. Can you guys hear me okay? All right. So today, I'm gonna go ahead and show you where to find the notes for what we're gonna do next. Okay, so I've put a new unit folder up here under Unit 6. So if you go ahead and take a look in there, I'm gonna do some notes that are part of the foldable. So if you get a chance and you want to print out the foldable, feel free. It's already there under Unit 6 foldable. The first homework is already posted too. So once we finish up today's lesson, you can go ahead and work on it. I will then upload the notes. So for now, it's empty. So once we're done, I'll upload it as well. I need a face cam, and then the video, I'll also upload the link to the video once we're done. So no face cam because I'm writing on the tablet. So if I did, you would just see like the bottom of my chin today. Okay, since I need to write. All right, so it'd be a little weird. All right. Okay, so let's go ahead and get started. I hope everyone's doing well today. I know there's been a lot of news, but we're just gonna control what we can control, right? So let's go ahead and get started. All right. So let's start with the first thing. Okay, so today the formal notes are going to be notes 35, the imaginary number I. Okay, so this will be the first set of notes for this unit. If you are going to follow along on the foldable, basically if you have everything laid out correctly, it'll be under the flap number 2. So let me give you an idea of where to look. But just go ahead and copy down the notes now. Don't worry too much about like the foldable. It'll be basically the same thing that's on there, but on the notes instead. Okay, so the first thing that I want to address here with the imaginary number is that the imaginary number basically here is something that comes separate from the realm of real numbers. Okay, so I want to draw a little diagram first to kind of explain what are all of the different numbers that exist in the world of math, right? So if you think of all the numbers that exist, okay, both real and imaginary, you have this division here between real numbers and then complex numbers. Okay, now most of your lifetime you've worked with real numbers, meaning these are your integers, these are your rational numbers. Your rationals are basically your fractions, right? So any number that could be created as a fraction would be considered a real number. So that includes all the decimals as well. Every possible number that is a decimal comes from a rational, okay, because it can be set up as some type of fraction. Now the ones that can't be set up as a fraction are numbers like pi. Those numbers are still considered to be part of the real numbers. Okay, so all your whole numbers, your decimals, your fractions, pi, those are real numbers. Okay, now where does an imaginary fit? Imaginary fits on this side. Okay, you have imaginary numbers, not 20 boxes. Sorry, 1, 2, 3, 4, 5, 6. You could probably get away with like 6 on the first page and then like another 4 on the second page. Okay, sorry. Okay. So you have imaginary numbers that fit in the realm of complex numbers. Now, complex numbers take the shape, and we're going to get into this a little bit more detail on the next lesson, but they take the shape in a plus b I, right? So notice that the complex numbers included in them, they have to be written in this way, in that they have a number a plus some number times irrational, right? Not the irrational, the imaginary, okay? Now the imaginary specifically is just this part of the number, this part of the complex. Okay, so complex is split into 2 parts. The imaginary is like the second half of the number. Okay. All right. So we're going to deal with this imaginary number today. Okay, so just to give you an idea of where that fits. All right. So the first thing in the first definition for I is the number I, okay, is the basic element of the set of imaginary numbers. Okay, so I is the building block. It's the smallest component. Think of it as like your unit value, the basic element of the set of imaginary numbers. So everything else can build up from them. Okay. So the way we define it, okay, the definition the definition of I is, well, that I is equal to the square root of -1. Okay, so there's a reason why this entire time we've been saying that if a negative appears inside of the square root, it falls into the imaginary, right? It becomes an imaginary number. Well, there it is, right? You can see why I is defined as something where it's the square root of a negative number. Well, it's the square root of a -1, right, in particular. Okay, so the reason why this is important is because from knowing this piece of information, that the definition of I is that it's equal to the square root of -1, there's so much we can do with it. Okay, so now we can find out things like, what is the value of I squared, or what's the value of I to the third, I to the fourth, I to the fifth, right? Because we know that basic definition, right? So I want you to think about what happens next if we try to find I squared. Okay, what would I squared be? Well, I could take I know that it's equal to the square root of -1. And if I wanted to know what the value of I squared is, then at this point, I can square both sides. Okay, by doing that, I know that I squared is going to equal, well, then on this side, I know that a square root and a square are the inverses of each other, so they cancel out, and we're left with I squared is equal to -1. Okay. So it becomes a pretty powerful tool now, because we know that anytime I see I squared, then I can just simply convert I squared back into a number, which would be -1. Okay, and there's a lot that I can do with that. Okay, now what about if we wanted to look for I to the third? Okay, if you think back to your properties of exponents, you can think of this as you can break this up essentially as, what if I to the third is the same thing as I squared times I? Right? You would agree here that I squared times I, here I has an invisible power of 1, right? So that's just I. Well, you already know now that I squared, that's -1. And you know that I, go back to your definition, is the same thing as the square root of -1. So now, remember that you cannot multiply outside numbers with numbers that are on the inside of the square root, okay? They have to stay separate. But because you have a negative times the square root of a -1, then essentially what it becomes is this. It's the negative square root of -1. Okay, so that's what we get for I to the third. Now you might say, like, well, what's the use of knowing what I to the third is? Well, in some cases you would need to be able to evaluate it. But the important part here is to show that there is a level of repetition that occurs with the value of I. Because once we get now to I to the fourth, I want you to see something here. That I to the fourth can be very easily written as I squared times I squared. Okay, we know that I squared is -1. So it's -1 times -1. When you multiply them together, that's just 1. Okay, so there's value in knowing the pattern of repetition. So essentially, I is stuck between only those 4 values. Okay, either you are I to the first, you're I squared, I to the third, or I to the fourth. Because, right, watch what happens when you start to go above that. Right, let's say now we were looking for I to the fifth. Well, you can break this up, right? You could say that I to the fifth is the same thing as I to the fourth times I. I to the fourth, you already know what that is. You already know that I to the fourth is just 1. And you know what I is, right? You know that I is the same thing as the square root of -1. So then when you multiply 1 times the square root of -1, multiplying by 1 won't change it. So what's your answer? Square root of -1, right? So notice, you are back to where you started, right? Once you cycle through anything after the power of 4, the next one will just start to repeat. Okay, so here I to the 5th gives you the same thing as I, right? That's why I highlighted them in blue. Okay, they're both the same. Right, now imagine I to the 6th. Well, think of the way that you can easily split that up. Once you've gone past 4, it's I to the 4th times whatever remainder is left over, right? So I to the 4th times I squared, right? You know that I to the 4th is just 1. So now really it's just I squared. Well, what's I squared? That's -1. So then this is equal to -1. Okay, so let me erase this highlight over here so that you can see that now I squared is the same as I to the 6th. Okay, so you see the repetition continues over and over and over. Okay, so the same would be the case if we went to I to the 7th, right? So without having to do the work, you can see how then I to the 7th, I to the 4th times I to the 3rd. Well, you know I to the 4th is just 1, so your answer is just I to the 3rd. I to the 3rd, negative square root of -1. And then when you cycle back over, right, you see the cycle now. When you get to I to the 8th, that's just I to the 4th times I to the 4th, right? Which is the same thing as 1 times 1, which is equal to 1. Okay, so the whole point of showing you this is that there's a cycle, that there's only so many answers you can get when you're dealing with I, with the power of I. I'm sorry, with I as a base. No matter what power you get to, essentially, if you can break it up into a group of 4 times a group of something else, then it just becomes a very simple process, right? You're only stuck between those 4 answers, right? The 4 answers that we got in these first 4 here. Okay. So we'll spend a little bit more time on this later. But for now, this is just like a quick introduction. Alright, so now let's actually do something with it, right? So let's actually try to clean up some of these examples. So for example 1 in your third box, notice that this is something that typically in a previous lesson we would have said imaginary, and then we would have stopped. But now we actually have a tool that helps us break this down a step further, because we know that anytime I have a negative inside of a square root, I can pull out the I, right? I can pull out an I instead. Okay, so here let me talk a little bit about a property of radicals that's going to help us break some of this up. There's a property of radicals that says that the square root of a product, such as A times B, can also be written as the product of A, square root of A, times the square root of B. Okay, it works both ways. This is a two-way street, meaning that if I have them separate, I can multiply them and they both go inside of the square root. But if they're already as a product, then you can split them apart. So think about how this can work for us. If I have the square root of -3 and I want to break this up, well, that's also like saying the square root of -1, or I'm sorry, the square root of 3 times -1. So then how does that help? Well, now what I can say is this is the square root of 3 times the square root of -1. The square root of -1, that is the thing that we can simplify. We can't simplify square root of 3, right? We're not going to turn it into a decimal. We're going to leave it in radical form. So I can bring down square root of 3, and now I have square root of -1. Well, what is that? That's just I. Okay, now I want you to notice something. I'm going to draw a tail right here behind the 3. I'm going to close it, meaning that the 3 is inside my square root and the I is on the outside. Okay, that has to be very clear. If you put the I inside of the square root, that is wrong. The I has to be on the outside. Okay, so inside, I is outside. Okay. Okay, so this is essentially our simplified version, right? This is our solution. Okay. All right, let's move on to example 2. Okay, so again, if there's any questions, please go ahead and ask on the chat, and I'll try to get back to it. All right, so for example 2, let's take a look at something a little bit larger. So what if you had the square root of, let's say, -98? Okay, and you want to clean this up. Okay, well, first thing is always take care of the I, or the negative, first, right? Transform that number into an imaginary. Okay, so what we can do here is say, well, this represents the product of 98 times -1. Okay, because it's a product, what you can do is then break it up into 2 square roots. The square root of 98 times the square root of -1. Okay. Now that you have the square root of -1 isolated from the 98, this then becomes your I, while still having square root of 98, okay, inside of a square root. How did I get +3? Okay, let me go back. Okay, so how did I end up with +3? So I broke up the product here. I know that in order to have a number like -3, it has to be the product of a negative number times a positive number. So what I did is then I broke it up as 3 times -1. Okay, because the product of 3 times -1 is -3. By me being able to break it up, then I can use the property, right? This property right here, that I have a product of 2 numbers. I can split them apart. By splitting them apart, I'm allowed to then take this square root of -1. That becomes my I. Okay, since the other factor 3, right, it's just the square root of 3 now, it stays as the square root of 3. Okay, so I'm basically just bringing that part down. What I'm trying to simplify is trying to get the negative out of the square root. When I take the negative out of the square root, I have to automatically add the I to the outside. Okay, good. So let's go back. All right, so same idea, right? Now the problem is that 98 is a number that is not prime. Okay, we don't know the square root of a number like 98, but you can simplify it. So this is where factor trees come into play. Okay, now the reason why we can't leave square root of 98 is typically by convention you want to simplify as much as possible. So here's where you start to look for factors of 98. What are the numbers that I can multiply to be 98? All right, well, if you ever get stuck, you start with the smallest numbers that you can think of possibly. Okay, so for example, 98, that could be 2. You could divide it by 2 because it's an even number. So if you divide by 2, then the leftover would be 49. Then you look at 49, right? Because you've already factored down 98, scratch it out, because then that's no longer an active number, right? You're not trying to simplify that anymore. Now you're only working with 49 and 2. 2 can't be factored any further because then it would just split into 2 times 1, right? So it's already prime. But 49, you can split that up. That's 7 times 7. Okay, so now scratch out 49 because it's no longer an active number. Okay, so now here's what you do. If I'm trying to find a way to rewrite the square root of 98 as something else, you look for a pair. You look for a pair. The reason why you look for a pair is because if you go back to this square root, remember, square root means that it is the opposite of a square. So an opposite of a square root, there's a power of 2 that's in there somewhere, right? So what we're looking for is 2 of the same number, right? If I have 2 of the same number, I can group them up. And then here's the analogy that I like to use. If I have a pair, if I have a buddy, 7 times 7, then that means I can escape. So you got to think of square root as jail. You can't escape unless you have a partner to help you. You got to have a partner of the same number. So then what happens is 7 gets to go on the outside. Meanwhile, the number that's left over that could not escape, such as the 2, because it didn't have a partner, that number stays inside of jail. So it stays inside the square root. Okay, and then you drop your I. Okay, so it's a rewritten version of the square root of 98, but now it's in the simplest form possible. Okay, now let me show you another way. Let's say a little bit more kind of a algebraic approach, right? The factor tree and what I use here, it's a little bit of a shortcut, but let me show you how you could achieve the same thing and why you get the same answer, why you're able to pull a 7 out. Think of the square root of 98 as the square root of the product of 49 times 2 with your I on the outside. Because 49 times 2 is a product of two numbers, you can split it as the square root of 49 times the square root of 2, and then the I still on the outside. Okay, well now square root of 49, isn't that 7? So then this becomes 7. The square root of 2 cannot be simplified, so you get square root of 2, and then you still drop the I. Okay, so that's the reason why that little trick that I use, where if you have a pair, you can pull it out, is because that pair represents a number that does have a square root, right? So then that's why here we get the same thing. Regardless of the method that you choose to do, you get the same thing. Now, what might be difficult is to think of the product of 98 as 49 times 2 right off the bat. So that's why the factor tree is helpful, because it just helps you break it down into the smallest pieces. And then from there you look. All right, let me find another example similar to this so we can practice the factor tree a little bit more. Give me a second. Okay, so let's try the square root of negative 48 for this one. Okay, so square root of negative 48. Okay, so again, first thing first. Okay, from this point now, you should be able to make that connection, right? I have a negative inside, that means that then this simply translates into I on the outside. Okay, so remember, this splits. This is the same thing as the square root of 48 times negative 1, which means we get to split this as the square root of two different numbers, square root of 48 times the square root of negative 1. That's how I'm able to remove the negative and it becomes an I that hangs out on the outside. Okay, now 48 does not have a perfect square root, unfortunately, so we have to go through the factor tree process. Now, in this case, right, think of 48 as, alright, well, let me try to factor this down into what I know. I know that 48, most likely, you might think of 4 times 12. Okay? Now, you don't have to factor everything. Remember, what you're looking for is essentially a pair. Your goal is to try to get a pair of numbers. So you could factor the 4 into 2 times 2. But then it's going to make you factor the 12 into all the way down as far as possible. So instead of doing that, start with the 12. right? Think of a way that 12 can be factored so that includes a 4, because if you can find a factor of 4, now you have a pair. So what if you factored it as 4 times 3? Okay, 12 is no longer active, 48 no longer active. Now you could continue to factor the 4 into 2 times 2 and the other 4 into 2 times 2, or notice what you can do here, you can stop because you have a pair of 4s already. The 4s don't have to hang from the same branch. You just have to find them somewhere as part of the tree. Okay, now because that is the pair, 4 gets to escape, so 4 goes outside. Who's the loner? That's 3. Okay, you can't factor him anyway, so then he's boxed in, he stays inside the square root. Okay, and then you drop your I. Okay. Now, why does it work? Why is it that that is the answer? Because if you take the algebraic approach, you take 48i, well, square root of 48, you could think of this as 16 times 3i. Well, then that becomes square root of 16 times square root of 3i. Okay, and so then square root of 16, that's your 4. Square root of 3 stays the same. Then you drop the I. Okay, so notice I'm getting the same thing. It's just that with the factor tree, I can do it without knowing my perfect square roots. Whereas the algebraic approach, I have to know them, right? I have to know the square root of 48 becomes the product of 2 numbers. One of them is going to be a perfect square. Okay. All right. So any questions there? Okay, let me know if anything comes up. All right, let's move to example 4. Now, example 4, this is where we start to utilize what we know. We start to then combine it with something else. Okay, so far it's just been a simplification process. Now, what do we do now if we have to take a product? Okay, take a product of 2 numbers, right? 2 imaginary numbers, right? How does it work? Well, let's say you're given the square root of -9 times the square root of -25. Okay, I want to emphasize something here. I want you to make a star and make a note, because if you do multiply them, you're going to get a number that is incorrect. Okay, the I on the outside. Okay, we've gone through the long way, but this is the shortcut, right? From here you can see how if I pull the I outside, now my 9 turns into a positive. The same thing here with the 20. Okay, so now square root of 9, that's 3, right? We can do that pretty easily. So now we just have 3i times square root of 25, that's 5, right? So you got 5i. Now you can multiply these together. Okay, this is a product. Now you're going to multiply the 3 times the 5. Okay, you're going to get 15. You're also going to multiply I times I. Okay, what does that give you? That's I squared. Okay, this is why I went through the process of that really long example, right, where we looked at all of the different I values, right? Now you know I squared is equal to -1, right? So we're basically going to reuse what we know right here to then transform that I squared back into a number. So we have 15 times -1. Then that's going to give us -15. That is my expression. Okay, that's what it's worth. Okay, now what would have happened, let's say, if you would have multiplied first? So remember, I told you that you need to extract the I first. This is the correct way to do it. What would have happened, let's say, if you didn't? Well, let's pretend. Right, so here, I'm going to do it in red. This is the wrong way, okay? But I'm going to show you why it's wrong, because it does lead you to a different answer, but it's a common mistake. Let's say you would have started by saying, okay, I know that a square root of -9 times the square root of -25, I know that I can multiply the numbers together on the inside, right? Supposedly. Well, when I do that, I get the square root of negative times negative, that's a positive. So it becomes positive 225. Okay, you can take the square root of 225. Right? Here we got, let me look for it. Where'd it go? Never mind. I know what it is. It's the square root of 225 is going to equal 15. Right? But notice how this number is different from what we got the first time. Okay? This property right here is tricky. Okay? It only works with real numbers. Okay? So you cannot multiply the negative of a square root times the negative of another square root to then suddenly become a positive real number. Okay, so this right here is the wrong way. Do not do this. Remember to extract the I. Okay. Any questions there? Yeah, I'll post the notes, and then you can always go back and rewatch what you missed. It's live, but you can always go back and then you can just watch it at your own pace. Okay, so don't feel like you have to watch everything as it goes right now. Alright, let's keep going. So now let's go on to example 5. Okay, so now example 5 starts to look at something else, right? So we took a look at a product. Now we're going to take a look at a quotient. Okay, let's look at a quotient that involves imaginary numbers. Okay, so let's say you're given an expression such as 4 over 5i. So I'm going to kind of take a little detour here. And remember when we looked at a complex number? Okay, it had the form a plus b to the I. Now the key thing about this is that if you are going to have an imaginary number, or a complex number, the key thing is that I needs to be in the numerator. I cannot exist in the denominator. Okay, so this process that we're going to go through right now is called rationalizing. Okay, rationalizing is the process of getting the I out of the denominator. Okay, and rationalizing is common in other types of problems. Like if you have a square root in the denominator, there's a way to get the square root out of it. Very similar to what we're doing here. So the process is to just get rid of it so that we can move it into the numerator. All right, so how do you do that? Well, it's a pretty simple thing. You look at what you have in your denominator. Well, currently it's just 5i. So what you're going to do is you're going to multiply by that denominator to the top and to the bottom to your original expression. Okay, so you're multiplying by 5i top and bottom. Why is this okay? Right? Because 5i divided by 5i is like multiplying by 1. Right? So if you can multiply by 1, you're not changing anything. Okay, so it's just going to rewrite it into a different way. Okay, so now you just multiply straight across. 4 times 5i, well, you can still multiply the 4 and the 5 together. That's going to give you 20i. In the denominator, very similar to what we did before, I can take this 5, multiply times this 5. That's going to get me 25. We can multiply the I times the I, and that's I squared. Okay. Now, from here, don't try to cancel the i's, because then it gets you back to where you were. Right? You're going to end up with one I in the denominator, so don't simplify the i's. What you do instead is you convert the I squared. What do you know I squared to be? I squared is equal to negative 1. Right? So this is why we rationalize, because then it transforms the I squared into negative 1. Right? So think about it. Now we get 20i all over 25 times negative 1. So by doing so, now what you have is 20i all over negative 25. No longer do you have the I in the denominator. Now it's only in the numerator. Okay? So from there, the only other step is I can still simplify 20 and 25, right? Pretend like the I isn't there. 20 over 25, you can divide both numbers by 4. I'm sorry, you can divide both numbers by 5. So if you divide top by 5, you're left with 4. You divide the bottom by 5, you're left with 5. So really, your final answer is negative 4 over 5i. okay, with an I in the numerator, which then leaves it in a form that is okay to be considered a complex number. Okay. So there's our answer. Okay, so what we did here is called rationalizing. Okay, so if I bring up the term we need to rationalize, that means I got to multiply my fraction by something. Typically, we just multiply it by the existing denominator, right? That's why I multiplied it by 5i over 5i, okay? Okay, so let's move on. Okay, let's take a look at a slightly more advanced version of rationalizing. Okay, so let's start here with 10 all over square root of negative 5. Okay. What do you mean by 4 is this limit? I messed up, okay? Relax. I meant to say 5. Okay, so let's start here, right? So we got to do a couple things here. First of all, we know that the square root of negative 5, we can make that conversion, right? We should, what's the first thing we do? We extract the I. Okay, that's the first thing. Whenever possible, extract the I. So that still leaves us with 10 in the numerator. In the denominator, now that becomes square root of 5 times I. Yeah, that is the answer, okay? Because here you're just asked to simplify and to rationalize, okay? So once you get it into a form where I is no longer in the denominator, then that is the answer there. Okay, moving back. So now, here, notice what I have in my denominator. I have an imaginary in the denominator. So what do I need to multiply by? I need to multiply by my denominator, okay? So in this case, I gotta multiply by the square root of 5i times the square root of 5i. Okay. It looks more complex. It's not too bad. Okay, so now let's focus here on the numerator first. Remember that 10 is an outside value. Okay, 10 is a whole number. 5 is the inside of a square root. Those numbers do not mix. They don't multiply. So really all we do is we just write them next to each other. 10 times the square root of 5, and you bring the I with you. Now in the denominator, there's a couple things that can be done. Okay, so look, here I have a product of the square root of 5 times the square root of 5. Okay, remember that the property that we talked about earlier mentions that if I have the product of two numbers, they're both inside square roots, I can multiply them and stick them under one square root. Okay, so I'm going to do the same thing here. This one then allows me to write this as the square root of 25. Okay, and then in addition to that, I can also multiply I times I. Okay, then that gives us I squared. So then, again, don't cancel out the i's, because then it takes you back to where you were, and all the work you did becomes pointless. Okay, so instead, leave the numerator alone for now. Square root of 10 times square root of 5i all over. Now square root of 25, that's your 5 right there. Okay, I squared, you make the conversion from I squared to negative 1. So now here's what you're working with. You have 10 square root of 5i all over negative 5. Okay. So now one last step to clean all this up. Think of 10 divided by negative 5. What would that give you? Right? So you can still divide these whole numbers. Right? Divide the whole numbers. So then that leaves you with 10 divided by negative 5 would be a negative 2. Okay, now that number is a numerator, right? Because if you were to divide, right? Imagine you divide negative 5 by negative 5 and you divide 10 by negative 5. That leaves you with a negative 2. Then the rest stays with you. So now here is your final answer. Okay. How are we doing so far? Are we okay? Does this make sense? Okay. If this part lost you a little bit, think of this as being 10 over negative 5 times square root of 5i. Right. So then this is where the 10 over the negative 5, that's where I got negative 2 from. And then square root of 5i. So again, you're left with a number now that has I in the numerator. That's how you know you're done. Okay, you no longer have the I in the denominator. All right, we're doing good. Okay, good feedback, sounds good. Okay, so now let's go ahead and let's take a look at one more example. I believe this is the last one. So for example 7, let me pull it up here. Okay, so we're gonna start with two different radicals. We have radical 24 all over 7i radical 2. Okay. All right. So now we can go ahead and say my problem is that I have an I in the denominator, right? I have an I in the denominator, so I need to find a way to get rid of it. Well, if I have an I in the denominator, I need to then multiply the entire fraction by my denominator, okay? So that means we multiply top and bottom by 7i radical 2 all over 7i radical 2. Okay, so we're going to break this up. We're going to do it by parts, okay? So first things first, take a look at the numerator, right? I have two numbers inside my square roots. Square root of 24, square root of 2. Okay, the numbers inside the square roots we can multiply together. Okay, everything else I cannot multiply inside of a square root. Okay, so we're going to rewrite 7i, but now inside of my square root I can take the 24 times the 2, that becomes 48. Okay, so now denominator, same process, okay, but now you have a couple more things to consider. Whole numbers, like 7, multiply with whole numbers. Okay, so 7 times 7, you're going to get 49. Okay, you have I, so you can multiply with I. Okay, so I times I, there's your I squared. And then you have numbers inside square roots. So you got square root of 2 times square root of 2. That's going to give you square root of 4. Okay, so at the moment you clean up everything in the denominator first. Okay, leave the numerator alone. Remember not to cancel any i's out. All right, so still have 7i square root of 48 in your denominator. Watch this, that's 49. I squared, you make the conversion, that's negative 1. Okay, so 49 times negative 1, and the square root of 4, remember these are all products. So you have 49 times negative 1 times square root of 4. Now that's a 2. Okay, so now let's keep going. I have the 7i square root of 48 all over, well, that's going to be negative 49 times 2, so that's negative 98. All right, so the goal has been obtained where we have I in the numerator, okay? Now the problem is that square root of 48 can still be simplified. So we need to take care of that first. Okay, I'm going to do a little bit of a revision here because I don't like I in the middle between 7 and square root of 48. So first I'm going to change it to 7 square root of 48 with I at the end, okay? All over negative 98. Now, we did the square root of 48 already. We did it in like example number 3, I think. Let's use what we know. Okay, we know that 48, if we were to do a factor tree, is the same thing as 16 times 3. 16 is 4 times 4. So now 4 is what groups up. 4 escapes. 3 stays inside the square root. Okay, so now let me just rewrite this. We have 7 Now instead of square root of 48, okay, this becomes 4 root 3. Okay, so now it's 7 times 4 root 3. And then I drop my I. All over negative 98. Yeah, it's allowed for me to move the I, if that's what you're asking. Because I typically should be at the end of the number. For the entire time before that, I left it there just for simplicity's sake. But eventually I needs to be pushed to the outside. So once I had gone through that entire math, I wanted to move it there to leave it in the location where it should be. Okay, so now, right, we go ahead and I can multiply whole numbers in my numerator. Now I have 7 and I have 4, right? These numbers are on the outside of the square roots. We can multiply them together. That becomes 28. Square root of 3 I, all over negative 98. Okay, so finally, right, the only thing left to do now is I have to find a way to simplify 28 divided by negative 98. Okay, I gotta look for a common factor that can divide both. So we can search for it. I believe here they both have 14 in common. I know 28, 14 can go into 28. 14 times 7, yeah, 14 times 7 gives us 98. Okay, so if you divide by 14, that gives you 2. If you divide this by 14, that gives you 7. So now what you have is negative 2 square root of 3I all over 7. Okay, or you can leave the negative in the middle, right, just to show that this is a negative value, right? I don't want to lose this negative in the denominator, but typically we never leave an answer with a negative in the denominator. So one common way that it's written is that the negative gets put here in the middle. Okay, it's the same thing as saying negative 2 square root of 3I all over 7. Okay, but it's just one negative, it doesn't split into 2. Okay, how about now? How we doing? Okay. Do you guys want to see another example? Or do you feel confident? Okay, let's do one more. Let me see what I have. Okay, I have one. That's not, the numbers aren't too big. Okay, so let's try last one then. Let's try 16 over square root of negative 32. Okay, so right in this case I got 16 all over, I'm sorry, yeah, this is what I want. 16 over square root of, remember to convert, right? You want to extract the I, so then this becomes 32I. From there, what would your product have to be, right? Your rationalization, you have to get rid of the I in the denominator. So you want to multiply by the square root of 32I to both top and bottom. Okay. Inside and outside numbers, whole numbers with numbers inside the square root don't mix. So you got 16 square root of 32I all over, okay? Here you're going to get square root of 32 times square root of 32. So you're going to get a pretty large factor down at the bottom, square root of, let me see what you're getting. Okay, so 32 times 32 is going to be 1024. And remember to multiply I times I. So that's going to give you I squared. Okay. So this one's just going to require a lot of simplification. Okay, so here, remember, numerator still 16 over square root of 32, I. Denominator, square root of 1024. Okay, well, if I had to square 32 to get 1024, then that means that the square root of 1024 is 32. Okay, I squared, that becomes negative 1. So now I can start to clean some of this up. I got the 16 square root of 32I all over negative 32. And I can see here that 16 and 32, those could cancel, right? 16 goes into 32 twice. So if I divide both top and bottom by 16, this becomes 1, this becomes 2. So really what I have now is 1, well, 1, I don't even need to write it. So it's just the square root of 32I all over 2, right? With a negative here. Okay, now, square root of 32, that can be simplified a little bit further, right? Factor tree it, 32, same thing as 16 times 2. So 16 is 4 times 4. So that's your pair, right? So you get to rewrite 32 as this 4 square root of 2, right? These are no longer active, so 2 is the only one left over. So now you have a negative 4 root 2 I all over 2. Right? So now you simplify one more time. Okay, because 4 divided by 2, well, divided by 2, that's 1. Divided by 2, that's 2. So in reality, here's your final. Negative 2 root 2 I. Okay. How was that? Okay, so there's good ones on the homework. Probably they don't get any more challenging than like example number 7 and 8. Okay, we're not gonna try to do anything super crazy, but just understand that there's there's different combinations. Like you can make up these problems and then try to go through and solve them on your own. So later on we'll take a look at adding, subtracting, multiplying, dividing. Okay, and that's when it gets a little bit more intense. Thank you, Uriah, appreciate it. But other than that, do we still need to print out the foldable? If you would like to, you're welcome to do it. I printed one out for myself so that I can keep track. The way that it's on the PDF, you have to print them all out. You have to like turn the page, maybe glue it together, fold it. So if you can figure it out, feel free. I mean, if you want to, that's great. But you don't have to, because the notes that I just gave you right now is what's on the foldable plus a little bit more. Okay, so there's not everything that's on the foldable is what I just gave you. I gave you more. So it's up to you. You don't have to. But if you like the foldable, then feel free. Okay. All right. So with that, just let me open up Chrome real quick. So let me show you which parts of the homework I want you to do. And then if you run into any kind of issues with the homework, you can always just ask me. You can ask me. I can set up like a Zoom, like an office hour type of deal for next week, and then we could just like do some homework without any lag. So I think that's the benefit of the Zoom, is that there's no lag on it, versus like on YouTube I have like a 15 to 20 minute lag between the time that I say it and the time that you guys see it. So real quick here, homework is due when we get back. So right now, just stay on top of it. Don't let it pile up on you. Okay, so you see there is there's a few examples to look at. Okay, some of these are the ones that we did in class. So I want you to go ahead and try 1 through 12. And then again, you see the examples that we did in class. They do them again here on this worksheet. And then try to do 13 through 20. Okay, so I believe the challenging ones that you're going to hit are going to be between 17 and 20. Okay, those are probably the challenging ones. So this man's gone by the time we're reading this. If we don't come back, then there's going to be bigger issues besides homework. Okay, so we'll see how things go. But if the event that were to happen, then obviously I'll probably come up with something where you submit the homework, maybe take a picture, upload it, and then I'll just check it like that for completion. Okay, so if there are problems with the homework, we can do them on the next live stream. How about that? We'll do them at the beginning, so you can type in what questions you want to see worked out, and then I can just I can do them for us. Okay. Okay. All right. Well, keep in touch. I'll definitely I'll probably set up a Zoom on Monday just to kind of check in, see how everyone's doing. And obviously if there's updates that I need to give out, then I'll give them out. But if not, then we'll just kind of keep going and our usual routine with Monday Edulastic, or and then the rest of the week we'll just keep doing our live streams. Okay. Alright guys, well I'm gonna log off then. Hope you guys have a good day, I'm gonna try to just, relax and not think about too much. So I hope you guys can do the same. All right. So keep in touch. Send me a message if you need anything. All right. Take care.